I see that Armin did entertain you in the meantime. Supervisor, advisor, whatever. We just advise you guys, you do the work yourself. So, welcome to his Master of Science thesis defense. It took a little bit longer than the 3 quarters that usually we schedule for a Master of Science thesis project, but of course Armin did a little bit more work than usual master student would do. How we'll organize this meeting is Armin will present in 30, max 45 minutes the work that he has been doing. Then we have the opportunity to ask him questions. The committee that is sitting in the first row, usually, thank you, Chris, is not going to be asking questions in that first part of the meeting. After that, we'll retreat for a private meeting with you. Then we'll be asking our questions for half an hour, up to 5 hours. And then after that, we will ask you to leave us to discuss what we found with the work that you present in your thesis. And then hopefully this will result in a positive outcome of this meeting. So Armin, please explain to the audience and the committee what you have been doing in your master thesis.
Thank you very much, Noroozi. I am Armin Noroozi. I'm a student of computer engineering here in Delft University. As Georgie, my supervisor, already told you, I work on the Delfi-n3Xt project, which is a nano-satellite. And the title of my thesis is Evaluation Methodology and Systematic Selection of Microcontroller for this nano-satellite. So during this presentation, I will give you a very brief definition of what type of satellites generally we have, and then which category Delfi-n3Xt nano-satellite falls into. Then afterwards I will introduce you my work and the methodology that I used in this work, and then examples with evaluating microcontrollers, some samples here in the presentation, and by means of conclusion I will recap everything again. So let's go ahead and see what type of satellites we have. We have numerous satellites. We have a variety of them, each of them designed to do something. And this is based on their mission. There is a way that we can categorize the satellites. In this way, we categorize them based on their wet mass. Now, in this categorization, we have large satellites that weigh more than 1,000 kilograms. We have medium-sized satellites between 500 and 1,000 kilograms, and small satellites. Now, within the small-sized satellite category, we have more, within this less than 500 kilograms, basically, we have more satellite categorization. So what we have here is mini satellites, micro, nano, pico, femto. Delfi-n3Xt falls into the nano-satellite category, which means it weighs between 1 to 10 kilograms. Now, there is another concept here called the Cubesat. The Cubesat concept says that the weight of the satellite should be less than 1 kilogram. The volume of the satellite should be exactly 10 by 10 by 10 cubic centimeter. And all the components used in the satellite are commercial products from the market. An example of a Cubesat, of a nano-satellite with a Cubesat concept in mind, is Delfi-n3Xt. This satellite was built here. It was launched 2 years ago, and it is still in orbit functioning properly. So it was a success. The successor of this satellite is called Delfi-n3Xt. Delfi-n3Xt has more payloads. It has a modular design. And all modules and subsystems in the satellite are controlled by the onboard computer. The onboard computer is the brain of this satellite. What exactly does onboard computer do here? Well, it always monitors all subsystems constantly. Make sure they're healthy. Make sure they're all working properly. It handles data transfer between all subsystems. Everything comes through OBC. It synchronizes different systems and schedules their activation while the satellite goes into orbit. And of course it does much more like data handling the commands, making sure that everything is correctly going and everything. And how do we make, we're going to use a computer to do this, of course. How do we make such a sophisticated computer that can do all this? We're going to use a microcontroller for that. It's a system on chip. How do we use, which microcontroller do we choose for this purpose? Now, first let's take a look at what exactly is inside a microcontroller. Inside a microcontroller we have a processor, a memory, and a bunch of peripherals. Processors are, there are a variety of them. Right now you go into the market, you have CISC-based and RISC-based processors. You have the ARM processors, which are, in my opinion, they're phenomenal. They have high performance and low power and everything. They're very small. And we have other types. We also have flash ROM-based memories inside these microcontrollers. And a variety of peripherals. So right now we have so many microcontrollers in the market. How do we go to find the perfect one, the most suitable one for this nanosatellite? We need to find a way. So to do this, we go with a ranking system. In this ranking system, which we define it in this way, we give points to microcontrollers based on how well they can do a requirement, as I showed you the requirements before. Now I scored them between 0 to 5. 0 means it's not doing it at all. It's not possible for that microcontroller to do that. And 5, that it can perfectly do it. It's very good. Now that's for each requirement. What else do we need? We need for all the requirements, if you put them all together, we need to have a better system. So we're going to use weights to show the importance of each of these requirements. Now, the more important, the higher the weight. And then finally, we get the final score by multiplying the points a microcontroller gets to the weight, and then sum all of that up of that microcontroller. This gives us the final score of that microcontroller. Afterwards, we just check all the scores, we rank them, we order them, and we see which one has the highest score. So now let's take a look at the criteria. What exactly are we talking about when we say the requirements in our criteria? What is important here is the processing power. It has to be, the microcontroller has to have enough processing power to be able to do everything that it's supposed to. If it doesn't, it fails. If it fails in space, the mission has failed. It has to have low enough power consumption that does not fail the other systems of the satellites. Another thing that's very important is, and by the way, the numbers that you see on the other side are the weight of each of these criteria. So another important thing, it's extremely important, you have to have a watchdog timer on your microcontroller. This is, if you don't have it, if the microcontroller fails and it needs to be restarted, you cannot just go upstairs, beep, click it, and then restart it. It has to do it automatically. To do that, we use a watchdog timer. And nowadays, almost like 90% of the microcontrollers that are being developed, they have a watchdog timer in them for this reason. Now, this, we also need other requirements. We have other requirements, such as the Delfi-n3Xt satellite main bus is I2C. So that's also extremely important. That's why it also gets a 5. SPI interface is not that important on the OBC. Why? Because what uses SPI? The flash memory, basically any type of memory card. They use SPI communication. Other subsystems on the satellite, on the other hand, do use, such as ADCS, they will use a gyroscope, which is being communicated through SPI. But for the OBC, we might only have the memory card. We have A to D and D to A converters because of the sensors and actuators that are being used for voltage monitoring, for instance. The OBC is monitoring system. So that's one of them. Also, a brownout reset circuit. It would be nice to have it. What does it do? It goes and checks the voltage. If it falls below the threshold of the microcontroller, it just stops the microcontroller, and when it goes back on the normal voltage, then it restarts it again. This is to prevent damage to the microcontroller. Now, the EPS, the electrical power subsystem of the satellite, is sophisticated. It can provide very good, stable power for the whole satellite. But in case something goes wrong over there, we still need to have protection for the microcontroller. Temperature range, of course, it has to be within the temperature range. Otherwise it's going to fail. And the past mission experience would be a plus for the microcontroller. If it's already out there and it has succeeded, then it gets more points because it's good enough. It's improved. The type of memory, as I said, we have flash or ROM memories. Now, if it has flash, it's better. So we put it as a criteria here. If it has ROM, then we can only write once on it. And when we're developing the satellite, when we're writing programs for the microcontroller, we have to write and write and write. That doesn't go good with the ROM. That's better to have a flash. Packaging is important. We don't want big microcontrollers to be there. It's going to use a lot of space on the satellite, on the system boards. SMD packaging is preferred because they're small and like ball grid arrays. They all have their pins underneath the chip, so it's better. And last but not least, the development environment. We need to do a very good debugging of the program that we're writing. On the design time, we do debugging. But when we are on the runtime, when it's actually on the microcontroller, we have to have access to the memory. To do that, we need a good enough development environment. Now, I'm going to give you some examples of how we apply this methodology on microcontrollers. Here I provided just 5 microcontrollers from the market. What I did was that I filled in this table. The 2 columns here are just, or 3 actually, they're directly from the data sheet. As we can see, the performances of each microcontroller is different from the other ones, obviously. Now, how do we rank them? As we said, we are going to give the highest score, highest point to the one with the highest performance, and then we go down. So if you look at this graph, you can see the one in the middle has the highest, so it gets a 5. The 2 on the left have 0.1 less than that, and the one on the right has 0.1 less than these 2. So that's a 5, these 2 are 4, that's a 3. And this one has the lowest, so we just give it a 1 on that. So with this in mind, we have filled in this table, as you can see, 4, 4, 5, 3, 1. And that's it for the performance. For power consumption, let's go and see. We again fill in the table from the data sheet. We calculate the power consumption of each of the satellites, depending on the performance. So here I went with the milliwatt per MIPS, million instructions per second. So in here we see that for 1 million instructions per second, we have this amount of power being used. Now, the lowest power consumption, the better. We don't want high power consumption here. So, yeah. So we can see the lowest is again in the middle, the ARM processor from Atmel, and the 2 on the left have a little bit higher than that. It's only 0.5 more than that. The one on the right is much more than that. And the last one is extremely high. So if we look at this, if we give this one a 5 and this one a 4, this is much higher. It has a much higher difference than here. So it gets a 2, a 1, that's very low. And the other one is just a 0 because it's consuming 24 milliwatts per MIPS. That's a lot. And we fill in the table again, and we see we have 44510. Now we go with the operating temperature. DFTBA is up there, and it's the temperature change between -10 and +80. So we go here for the Delfi-n3Xt as well with the same temperature range. The microcontrollers that support this get 5. The ones that don't get a 0. What happens if you select this one? Doesn't it just get up? Well, let's say if it gets in, then what we have to do is to create some sort of a thermal management inside the nano-satellite, which requires a lot of human resources and everything. That's why it gets a 0. So lower the score. Now let's go to also with ABC and DAC. The ones that have it, the minimum we need is, and obviously is probably, let's say we need 4. Now all of them have at least 4, the ones that have ABC. So they get a 5, they have more than 4. Also this one, I forgot to put it here. And the ones that don't, they get a 0. The same goes for the D2A temperature. Now, after this we have I2C and SPI. Again, we need both master and slave modes on I2C. The ones that do not have a slave mode, what happens? Why did this one get a 0 that didn't have a slave mode? Because when the satellite is in orbit, if we want to control it manually from here, the satellite's brain is going to be a slave. It's not going to be the master anymore. We are going to be communicating with the primary transceiver, and then that's going to be the master. So if we're going to use the one that has only master mode and doesn't support slave, what are we going to do? We're going to use a bridge. Or we have to implement it somehow in the software, which again uses a lot of resources. So if you put a bridge, what happens? If you put a bridge, the space on the board is going to be used. Not only that, if microcontroller doesn't have I2C, like no master, no instrument, doesn't have any, what's the difference between that and the one that only has a master? Nothing. For both of them, we're going to use a bridge. So it looks just like that, so it's a 0 for that. Now, for the SPI, we already see that all of them have master and slave support, so we give them 1. Watchdog timer, it's very important. All of them have it, so they all get the points. The ones that do not have brownout get 0, the ones that do have it get their points. And past mission experience, we can see that the very first one is used in Delfi-n3Xt, and it's a success. So it gets points for that. The other 4 microcontrollers here are not used in the past space missions. So they don't get any points in this category, in this criteria. Also the memory. So the ones that have flash will get more points than the ones that have ROM, because on ROM we can only write once, as I stated before, and it will make it just a bit harder to develop it. So as you can see, the ones with the flash got a 5, and the one that has only ROM got a 3, because it's still usable. It's not a 0. It's not like it doesn't have any internal memory and needs external memory to work. So it gets a 3. And on the second one, it has both flash and ROM, but since it has flash, it's getting 5. Also, the packaging, as we mentioned, we need SMD packaging, and all this type of packaging that you see is a part of SMD, surface mount device. Now, they're very small, and therefore they're just great. They all get the 5 points. But if you look at the old microcontrollers, like the first packaging that we used, I don't remember the name, the big ones, the big spider ones. Dual link packaging. Something. Yes. So these are all SMD, so they get 5 points. And the development environment, you can see Code Composer Studio, the Essentials, Crossworks, and a variety of other third-party IDEs. Now, they all support both runtime debugging and design time debugging. That's great. They get 5. The very last one doesn't do runtime debugging, which is important, but it still does design time debugging, and it also does a simulation for us. So it basically simulates the whole environment for us, as if it is running. You still can use it. But it's not as good as the others, so it gets less points. We give it 3 here. Now let's take a look at the final score, final result that we have. And we put all those points inside this table. We do our multiplication for each of these rows, 4 times 5 plus 4 times 5 blah, 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 blah. And then we get the final score of each of the microcontrollers. The one that has the most is selected to be used, is a result, basically, of this methodology. So as we can see, the first one is used, has got the highest score. So in my work, also the same microcontroller got the highest score, and it was selected for this satellite. Now, until here, the work was done. In theory, we have everything. We have the perfect one, the most suitable microcontroller for this satellite. What else did I do? I went ahead and created, well, the prototype for it. In this design, first, of course, we started with schematics, and then we created the whole design. In the schematics, I created the PCB layout for the computer, for the microcontroller. And then afterwards, after it was finished, gave it to a company. They made the PCB, and I soldered all the components on it, and the whole computer was ready. There were 5 of these boards. All 5 of them were tested, and all the tests resulted in success, and it was working properly. And now they're just being used for development of the satellite. So, to recap everything, in conclusion, what did we talk about? First we started talking about the satellite, what Delfi-n3Xt is all about, and in Delfi-n3Xt, the problem was to find the most suitable computer that can do all the work of the brain of the satellite. If possible, we use it on other subsystems. That would be good. Now, what we made was a ranking system. In this ranking system, we started with the points and weight, and the final score was given by this system. Then we evaluated the microcontrollers, a lot of microcontrollers, and then one of them was chosen as the optimal choice. And afterwards, a prototype was created. So this is not only a step forward in creating better satellites for in the near future, but also there's another step forward in understanding the ultimate question of life, the universe, and everything. Thank you.
Thank you very much. Very nice presentation. Indeed. Questions? I see immediately.
First, thanks for the presentation. I have a question about your prototype. So you are testing all the requirements that you talked about in this prototype, right?
Yes.
Watchdog and
for every individual part of the, as you can see here are all the pins of the ports, basically of the microcontroller. We have the JTAG to program it, and we have, I put 2 high-frequency communication loss ports for it. Now, what I did was I created software, different programs, let's say, each of them individually checking every part of the microcontroller, checking the communication, just by one board itself. Now, after that, we put 2 boards and connect them. This one activates it, the other one reads it, and make sure everything is working properly. And then also there's a communication. For instance, the I2C comes. This one sends data, that one receives it, acknowledges it, sends it back. Also a whole, how do we say, complete test of the hardware all by itself. So a bigger software, a bigger code that activates all the peripherals on the microcontroller and starts testing them. That's what we do.
Thank you.
Any more questions?
Yes,
Please.
Was there a pre-selection for the processors that you chose?
was it?
Pre-selection. For example, was there some criteria that are definitely a no-go? For example, if the processor doesn't have a serial parallel interface or something, and then you just cannot use it even if it ranks high on all the other things? Or?
If that happens, we're going to use bridges. Now, it didn't happen. It's because of the way that we give them the points, and also based on the weight of each of the criteria, right? So in this, it didn't happen, and it won't happen because of, unless, for instance, let's say the one that is selected right now only lacks a serial peripheral interface. Now, if it doesn't have that, then and gets the highest score, then we're going to use a SPI bridge.
Okay.
Question?
Please,
Yes.
related to that one, if it doesn't have a, let's say, a digital to analog converter, what other, is it like a no-go, or you can, there are like external...
No, let's take a look at the points briefly. As soon as I find the mouse. Here. Yeah. So, you can see the weight of these two is 4. So, if your question was, if I get it correctly, that if it doesn't have this, the one that we just used,
Yes.
and it gets the highest score.
Yeah, that's
Yeah.
one of the examples.
Again, we're going to use an alternative. For instance, we use a bridge for it. Because if we need it,
Mhm.
and everything else is perfectly higher than the other ones, then yes. It is possible also to do another trade-off, but
So it's a trade-off, it's not
no, actually it's not. No, this is a trade-off, yes. The whole ranking system and everything is a trade-off.
So in case that the ARM 9 was, let's say, the best of
Yeah.
the best, then you could still use some...
Then we use that, and then we, whatever that it was missing, that is true. Yeah.
Okay. Please.
I have 2 questions. The first one is, did you actually look at the requirements of the satellite and try to estimate the processing performance that you needed? And second of all, is there going to be any sort of, let's say, non-volatile storage on the satellite that you're using? Or not?
Okay, that's a very good question. The second one first. There was a talk to use an external memory card on the satellite. So instead of which is for housekeeping data basically, not for the flight software itself. So that was your question. If we're going to use another one, yes. I'm not sure if the final decision was made to use that, but at the beginning we had that in the discussion. And the performance of the satellite, yes. Well, there are many ways to provide information about the performance. Now, some people use MIPS, DMIPS, or even flops or anything, depending on what we are making. Now here, the requirement was for the processing power.
No, but the question was, did you consider it?
Yes. Yes. But I don't remember what the number.
Okay. So we're done with the questions. Surprisingly, many questions were asked.
Very good. Very
I'm
good.
very happy because usually I'm asking myself questions to the audience. But this time this was not necessary. So if there are no more questions, I would propose that we thank Armin again. And as announced in the beginning, this leads us to the second part of this examination when the committee will be asking the questions, and this is a private session between you and us. I understand you reserved the meeting room on
Yes,
the
it is
15th
reserved.
floor.
So if you like-
So since maybe some of your friends would like to stay here and wait, I don't know what's the planning for the parallel session, so I would propose that we move to the meeting room.
Right.